So this video is also coming from section 15.1 out of the Musser book. And this will actually be a little bit of a throwback to probably your last algebra course, because this is all about slope. So if I take a screen on GeoGebra that does not have an axis on it, so this is just basic grid lines, and I draw a line, and I decide that I want the line to go, let's say, from that random point and go up 1 over 2, or up 2, sorry, over 1, up 2 over 1. Okay, I can put a point, up 2 over 1, up 2 over 1. You'll see that if I follow it as rise over run, I will consistently get to all the points that are on this line. So this is just one example of an increasing line. Okay, so it's going up as I go from left to right. Now I can also create a line, again, take a random place on the grid, and I can decide, okay, I want to go down 1 and then maybe over 3. Okay, let's plot the point. Down 1, over 3. Down 1, over 3. And I can see that as I keep moving in that fashion, down 1 over 3, I will consistently hit all the points on this line. Then again, this is using the concept of rise over run as the slope. Now, because I'm going down, it would be looked at as a negative change. So this one would have a negative slope. I could create another line that is perfectly horizontal. So maybe I want to start at this point and I just want to move horizontally. Now, I did not move in the y direction, okay, or rise, but I did run. So this has a 0 rise and it only has a run, meaning that the slope would be 0. And then finally, my last orientation of a line would be a perfectly vertical line. And let's again analyze rise over run. This would have a rise, okay, completely rises, but there is no run. So we'd have a rise of, let's say, 2 with these 2 points. We have 0 as a run. 0 is never allowed to be in the denominator of a fraction, and so this slope would be undefined. There's actually an error in the textbook. The textbook does talk about it having no slope, and that's actually not the correct terminology. You actually want to say that the slope is undefined for a vertical line. So these are your 4 typical orientations of lines, and this is what we're going to be exploring. So what we're going to do next is, if I put the grid back in, now we're going to take a look at calculating these slopes using the actual slope formula. So now that these actually have coordinates, let's label the coordinates. So this has the point 3,2, and then also on this line we have the point 5,6. So from what we did earlier, I was talking about rise over run. Well, I already can count that this has a rise of 4 and a run of 2, which is simply 2 over 1. Okay, so that simply reduces to 2 over 1. But how am I going to figure that out with the numbers? Well, very similarly to what we did in the other videos, I could take a look at the change in the y direction and the change in the x direction. So because rise comes first, I'm going to look at the difference in my y values. So I have 6 and 2. If I look at the difference between 6 and 2, I would get a distance of 4. And then for my run, I have 5 and I have 3. So my change in x would be 5 minus 3, which is 2. And so what I'm really saying is I want to look at the change in y divided by the change in x. And that's what gives me my slope formula. I could also do the same thing looking at my decreasing line here. So if I put in a point, this is the point 10, 8. And this is the point 13, 7. Well, rise and run. So I want to figure out this distance first. Well, if I want to get from 8 down to 7, 8 minus 7 is 1. Okay? But then if I go in the same direction of the subtraction, I would then have to do 10 minus 13. So that's going to give me a negative 3. And that's where my negative is going to come from, because I'm going to be going down 1 and over 3. We said it should be a negative slope earlier. So it's going to be negative 1 over 3 because of the decreasing motion, or the change, the negative change. Let's do the same thing with my horizontal line. If I show the two values, notice that my output, my y value, did not change. So if I do the change in y over the change in x, my change in y is going to be 3 minus 3, which is 0, over 10 minus 6, which is 4. But 0 divided by anything is 0, and so this slope is going to be 0. In other words, it is constant, it's flat. And then if I go to my vertical line and do the same thing and put in the values, I'll notice that my x value stays the same because there's only a change in the y direction. So if I try to do rise over run and look at the change in y, 9 minus 7 will give me 2, but 18 minus 18 will give me 0. And we all know that we can't divide by 0. I would have 2 over 0 here, and 0 in the denominator would make this undefined. And so all of this is coming from our slope formula. So what we just found is our slope formula, and slope is usually shown with the letter M. So our slope formula is going to be the change in y over the change in x, or in other words, y2 minus y1 over x2 minus x1. And this will be the slope of any line on your coordinate plane. So next we're going to talk about how you can relate slope to other concepts that we had seen from the past videos. So the next thing we're going to talk about is how can you use slope to determine collinearity. So it turns out that 3 points will be collinear if the slopes of the two short segments are equal. So for example, if I make a line segment PR with Q somewhere on PR, okay, what this is saying is if I find the slope of PQ and I find the slope of QR, if those two slopes are equal, then I know that PQ and R all fall on the same line. Now, in all of these theorems, they always have the exception of it being on a vertical line, okay, the slopes being undefined, but I expect you to know that that will always be a choice, that will always be an option. So at the heart of all of these theorems is going to be the one that I address here. So what we're saying is the slope from P to Q will have to be the same as the slope from Q to R. If we want to prove that, we can give these some ordered pairs. So if I make a grid, and it's just easiest if I make one at the origin, let's call P 0, 0, and let's call Q 2, 1, and let's call R 4, 2. Then according to the collinearity theorem, the slope from P to Q better be the same as the slope from Q to R. So let's see. We want the change in y, y2 minus y1, divided by the change in x, or x2 minus x1. So for PQ, it's going to be 1 minus 0 divided by 2 minus 0, or in other words, 1/2, or up 1 over 2. And then if we do the same thing for QR, I'm going to do 2 minus 1 over 4 minus 2, which will be 1 over 2, which will still be 1/2. So I will get the same exact slope connecting PQ, on the line connecting PQ, and on the segment connecting QR. This then takes us to slopes of parallel lines. So if we go back to GeoGebra, and take a look we want to take a look at how we can draw parallel lines. So let's say that I decide to make a line, and I'll just pick some points. I want the line to go between those 2 points. And I want to create a parallel line to this line. Well, and let's say I want that parallel line to go through this point. So this is just like giving us the same set of instructions. If I want to start at this point, how am I going to walk this line? So I'm talking about the slope. I'm going to have to go up 2 over 1. Up 2 over 1. So if I give this guy the same set of instructions, am I ever going to cross paths with this line? Well, let's see. Up 2 over 1. Up 2 over 1. I will never hit or cross this line, and so they are running parallel. They're always going to be an equidistance apart, or in other words, run like railroad tracks. If I want GeoGebra to show me that parallel line, I just have to select the 2, and look at that, it will draw a line that has the same exact slope as the line that I originally drew. And so that's our definition of lines being parallel, is that they have to have the same slope. So now let's talk about how you can tell if lines are perpendicular. So I'll delete my parallel line, and let's see if we can come up with how to decide if they're perpendicular. Well, first, let's talk about it being increasing here. So now we know that the definition of perpendicular is that they're supposed to cross at 90-degree angles. That was our definition up until right now. So what we're saying is that if this one is increasing, in order for it to go at 90 degrees, I know that this one is going to have to be decreasing. So hopefully that makes sense. The other thing that we can do is say, well, if I know that they cross at 90-degree angles, can I look at a 90-degree rotation of this line? So what we're saying here is you can either try to picture it being rotated 90 degrees, or you can, if you have it on a piece of paper, you could physically rotate it to be 90 degrees. But what we're saying is we want this exact picture to be just 90 degrees over here. Okay, that's what we're saying. So it's kind of obvious to see that if this is increasing, it's going to have to be decreasing for it to be perpendicular. But that's not quite enough because, for example, I could have a very sharp decreasing line, and I know that that's not crossing at 90-degree angles. So there's got to be something else. Well, it turns out that if you just invert the instructions, you will get perpendicular movement. So, for example, here we were going up 2 over 1, up 2 over 1. If I take the opposite and invert that movement, so in other words, take the reciprocal, I will create a perpendicular line. So let's go from this point. Okay, so before I was going up 2 over 1, now I'm going to go down 1 and over 2. Because remember, I'm negating it and I'm taking the inverse, and I'm taking the reciprocal. So if I start at this point and I go down 1 over 2, that actually looks pretty good. Okay, because what I'm doing is I'm making a perpendicular line right through this point. So let's see if GeoGebra can help us out with that and prove that that's the one that we're going to get. I want to create a perpendicular line through this line and that point. Well, interesting. That's exactly what it did. It went down 1 and over 2, whereas this slope was going up 2 and over 1. So it negated the slope and it took the reciprocal. There is a really great picture of this in your textbook. And I just want to show you that picture because I talked about inverting it. Or, I'm sorry, rotating it 90 degrees. So if you take a look at this page in your textbook, you can see that what's happened is they rotated it 90 degrees, so whatever was coming from this axis is now coming from this axis, and they're showing you that it is always going to be the reverse and opposite sign of the other coordinate. And that's your definition for perpendicular lines.